Hello everyone, welcome to the MUDE week of machine learning. In this lecture we are going to learn about the classic algorithm in unsupervised learning called the k-means clustering. What is k-means clustering and how to implement it? We will find out the answers together in this lecture. As learning objectives, by the end of this lecture you will be able to formalize a clustering problem based on centroids. Centroids are a new concept that will be introduced later in this lecture. Also, you will be able to explain different measures of similarity or dissimilarity in clustering, and finally implement the k-means clustering. There are three topics in this lecture. The first one is clustering based on centroids, which is a classic family of clustering methods. The second is a similarity of dissimilarity measures used in clustering. And finally, we will learn about k-means clustering. First, let's find out what is clustering based on centroids. So let's recall what is the problem of clustering. Given a dataset X, our goal is to partition the dataset into small numbers of clusters, k clusters in this case. Here we assume the number k is going to be given in advance. Now let's consider a two-dimensional dataset with variables x1 and x2. In this figure we plot the data samples as dots from the dataset. Let's look at how the data samples are located in this 2D space. We can notice that some samples are located close to each other, while other samples are located far away from each other. So let's take this circle data sample as an example. We can say that this sample is similar to another sample here pointed out by the blue arrow because they are located close to each other. And we can say this sample is dissimilar to another sample located a bit far away pointed out by the red arrow. In this way, we can find more similar samples and dissimilar samples in the 2D space, as indicated by the blue and red arrows. Here is where the idea of clustering emerges. By our intuition, a cluster can be a group of data samples whose interpoint distance are small compared with the distances to samples outside the groups. So the goal of clustering is to group close samples together into a cluster. As an example, then we can cluster the samples here into two clusters, C1 and C2. Note that it is also possible to cluster the samples into different and more clusters, depending on the clustering method we use or the number of clusters we want to have. With the goal of clustering in mind, how do we formalize this notion of clustering? To answer this question, let's first introduce a set of centroids denoted by the vectors uk, where in total we have k centroids because we want to find k clusters. We can think of the centroids u sub k as representing the center of the clusters. As examples, we denote the centroids of clusters C1 and C2 in this figure using circles. Here you can see how the centers are located in the center of the two clusters. In data of higher dimensions, the centroids become more difficult to visualize, but this is the idea is the same as in the 2D space. With the introduction of centroids, now we can update our goal of clustering, that is to find an assignment of data samples to clusters and a set of centroids, such as the sum of the squares of the distance of each data point to its closest centroid is as minimum as possible. Now, in order to have the k clusters, we need to find a way to assign the data samples to the clusters and also find a set of centroids of the clusters. But updating the goal of clustering, we can further formalize the clustering problem. First, let's see how we can assign the data samples to clusters. For each data sample x sub n, we introduce a corresponding set of binary indicator variables r sub and k. Here k is from 1 to capital K, describing which of the k clusters the data sample xn is assigned to. So if data sample xn is assigned to cluster, let's say lowercase k, then we have r and k equals to 1, while R of nj equals to 0 when the j is not equals to k. Then the goal to find an assignment of data samples of clusters becomes to find this set of binary indicator variables, because this set of variables define the assignment of data samples to the cluster, to the total number of clusters k. So far we have formalized the assignment of data samples to clusters as the centroids to clusters, and to formalize the problem of centroid-based clustering, given a dataset X, our goal is to find a corresponding set of binary indicator variables and a set of k-centroids, such that the sum of the squares of the distances of each data sample to its closest centroid is the minimum. Since we want to have the sum of the squares of the distances of each data sample to its closest centroid is a minimum, we can define an objective function j, also known as distortion measure. Here you can see j has two layers of summation. The first layer inside from 1 to k is the summation of all the within cluster square distances. So the square distances of all data samples belonging to a cluster are added up. The second layer of summation goes from 1 to n. That denotes that we are adding up the within cluster square distances of all data samples. In this objective function j, we aim to find values of the binary indicator variables r and k and the centroids uk that minimize the objective function j. Now we have formalized these centroid-based clustering problems to an optimization problem that aims to minimize the objective function j. Here are some important comments on the centroid-based clustering problem. In previous slides, we are assuming the number of cluster k is given. And indeed, some clustering methods assume the number of cluster k as a given variable. But for other methods, the number of clusters is a consequence of the method and certain definitions of thresholds. For the assignment of data samples, some clustering methods assume each data sample will belong only to one cluster, while other methods consider the probability of data belonging to a cluster, such as the method of fuzzy logic. Also, centroids are usually defined as the mean or center of the data samples in a cluster. But when working with more complex data structures, such as documents, data coming from images, videos, news, sound, we can consider the most representative data sample as the centroid. Going forward from here, we now have an optimization problem we want to solve. We still have two remaining questions to answer in order to find a solution. How can we determine the distance between data samples and centroids? And how to find the values of the r sub nk and uk variables? If you still remember, r and k are for data sample assignments and uk are the centroids. We will find out the answers to the next questions right away. Now, let's find out different similarity and dissimilarity measures we can use to quantify the distances in clustering. Let's recall the 2D datasets with variables x1 and x2. In this plot 2D space, we want to determine if the data samples are close or far away from each other in order to perform clustering. To quantify such distances between data samples and centroids, we can use similarity or dissimilarity measures. So what are the common measures, what are typical measures of similarity or dissimilarity? One of the options is to use what is called a cosine. It is a measure that considers the angle between two vectors. Here is the definition of the cosine between data xm and data xn, called theta mn. You may be familiar with this definition from the courses of linear algebra. For explanation purposes, let's consider in the plot three different data samples, x1, x2, and x3, indicated by crosses in brown color. Over here you can see theta 1, 3 is the angle between the vectors from the origin to x1 and x3. We can also calculate the angle between the vectors of x1 and x2, which will be called then theta 1, 2, and is shown in this plot. Then, when we compare the two angles, theta 1, 2 and theta 1, 3, it appears that both angles are quite similar to each other. So in that sense, x1 is similar to both x2 and x3. But now, if we consider the normalization of data samples or a different origin from the vectors, then the cosine similarity may provide a different information. And here you see the angles between the vectors of the samples when the vector origin is shifted. Now theta 1,2 and theta 1,3 are sufficiently different from each other, meaning that the samples can be treated as dissimilar samples. We can also quantify the similarity between two data samples using the classical distance metrics, the Euclidean distance, also known as the pairwise distance between two vectors. Here is the definition of the Euclidean distance between data xm and xn. In the plot over here, you can see two clusters, C1 and C2. In red color, we highlight one data sample in cluster C1 for explanation purposes. We can visualize the Euclidean distances between these samples to the other samples in the same cluster C1. In clustering, we want to have the calculated distances as short as possible so we can group the samples in the same cluster. In this plot, we can see now the distance from red sample to samples of the other cluster C2. In such a case, we want the samples belonging to the other cluster to be far away from the red sample. Here we are analyzing an important and sensitive property about where we define the boundaries between clusters. In this plot, you can see when the data samples are near the boundaries of clusters. They are going to be closer to the samples of the other cluster than to the samples in the same cluster. So we need to pay attention to how the boundaries between clusters are defined and how they are going to be affecting the clustering results of different algorithms in the literature. You can also find other distance metrics to measure similarity. For instance, the L1, LP, and L infinity distances between two vectors. Here are the definitions using xm and xn as the input. These are different distances that will lead into different characteristics for the clusters. Here let's take the two red samples as an example to demonstrate the different distances. This is the Euclidean distance as we defined before. In this plot, we can see the L1 distance, also called the taxicab or Manhattan distance. In this plot, the sum of the length of the two lines is the LP distance, which is somewhere in between of L1 and the Euclidean distance. And finally, the L infinity distance captures the maximum distance with respect to all the components of the vector. In this plot, it is indicated that by the length of this brown line over here. There are also measures of similarity using non-vector inputs, as in real-world applications that you will face in the future. Then a function d using xm and xn as input can be tailored to compute the dissimilarity between text, images, audios, videos, etc. With all the similarity measures in mind, we should understand the selection of similarity or dissimilarity measures that will determine the results of the clustering problem. The optimal choice is usually related to the application, so to the inherent characteristics of the problem or data that we are dealing with. Sometimes trying out different similarity measures could help to discover different hidden data structures from the clustering. Now, we have a clustering problem to solve, and we have similarity measures to quantify the distances between data samples. So let's see how can a classic algorithm, the k-mean clustering algorithm, find the clusters that minimize the objective function of clustering. So let's recall the goal of centroid-based clustering. Given a data set X, our goal is to find a corresponding set of binary indicators variables R and K and a set of K centroids that minimizes this objective function J. Basically, the objective function J is the total within cluster distances of all data samples. In k-means clustering, we assume the number of clusters k is going to be given as an input. To begin with, the k-mean clustering algorithm first chooses some initial values for the centroids uk. These values can be randomly generated or manually selected by us. Then, a two-step iterative procedure is performed until j is minimized, or what we call until we converge. This two-step iterative procedure is the core of k-means. The first step is to minimize with respect to r and k while keeping the uk fixed. The second step is to minimize j with respect to uk while keeping the r and k fixed. This sounds very abstract, but let's see how exactly this iterative procedure works. In the two steps, we're updating the samples assignment variables r and k and the centroids uk. These two steps correspond to the expectation and minimization steps of the well-known EM algorithm. If you're interested in the EM algorithm, you can find more details in the recommended reading materials for this lecture. For now, we will call the two steps the E step and the M step respectively. Let's find out what exactly happens in the E and M steps of k-means. In the E step, we want to minimize the objective function with respect to data assignment while keeping the centroids fixed. Essentially, in this step, we need to assign data samples xn to the closest centroids. This is because when the centroids are fixed, we want all data samples assigned to their closest centroid, so the total distance from samples to centroids is minimized. So mathematically, we update the assignment of data samples r and k using the argument of the minimum square distance between the samples and the centroids. Now in the M step, we want to minimize the objective function with respect to the centroids while keeping the data assignment fixed. Here, because we just updated the data assignment r and k in the M step, we can now update the centroids uk by calculating the mean of all the data samples assigned to uk. So we can use this division here to update uk. It is the sum of all data samples in cluster k divided by the number of data samples in cluster k. By iterating between the E and the M steps, we will eventually minimize j until it cannot be further minimized, so till it converge. Let's visualize the k-means clustering algorithm in action using an example. On the left of the slide, we briefly go over the algorithm again. So k-means first initialize k centroids randomly or manually, then it iterates between the E step and M step until the objective function j is minimized. The E step is assigning all samples to their closest centroid, and the M step is updating the centroids by calculating the mean of the samples assigned to the centroids. So let's use the data samples in this figure to see how k-means works. First, at iteration 1, we initialize the k centroids. Here we assume 3 clusters, so k equals 3. In the figure you see, we randomly generate 3 centroids indicated by the crosses in the 2D space. The objective function is not yet calculated since this is the first iteration. Now we go to the E step to assign samples to the closest centroids. By doing so, we obtain 3 clusters represented by 3 different colors. Now we go to the M step to update the centroids by calculating the mean of the assigned samples. By doing so, we notice the 3 centroids are located in the 2D space. This is the end of the first iteration, so we calculate the objective function j, and this is the result. Next, we start iteration 2 by the E step, assigning samples to the closest centroids. In this plot, we can see the samples are reassigned and new clusters are formed. Again, we go to the M step to update the centroids. In this plot, the centroids are updated. Then we calculate again the objective function j, and this is the result. Next, we go to iteration 3 by repeating the E and M steps. At this iteration, we find that the samples and centroids remain the same, resulting in the same value of the objective function j. Therefore, k-means stops, and we have our final 3 clusters shown in this plot. So basically, this is how the k-means is implemented. The concept of Voronoi diagram is often used to show the assignment of samples in the data space. The centroids and a distance metric will create a partition of the data space that can be visualized by the Voronoi diagram. This partition determines regions in which the data samples belong to their nearest centroid. Here you can see in 3 iterations how the Voronoi diagram changes with the centroid and updates the assignment of samples. You can pause the video here if you need it. Using the same dataset, now I want to challenge you with this question. Can k-means always find 3 perfect clusters like we just did when the initial centroids are different? Do you have an answer? You can pause this video if needed. To answer this question, let's see 2 different cases of initialization. In this first case, you can see 2 initial centroids at the bottom that are located too close to each other. As a result, the 2 centroids keep fighting for one group of data samples, and at the end, they end up sharing those samples, while the other centroid gets more samples. Now let's take a look at the second case. In this case, 2 initial centroids are located too far away from the data samples. In the end, no sample is assigned to the 2 centroids, while one centroid gets all the data samples. So with those 2 cases, now we know that the answer to the question is no. Now we can have some important comments on the k-mean clustering. First, there is no guarantee of k-means to converge to a global optimal solution, because the algorithm depends on the initialization. So to avoid undesired clustering results like we just saw, we should pick initial centroids that are far away from each other and are close to the data samples. Also, the selection of k, which is the number of clusters, will greatly impact the clustering solution. For some problems, k is well defined in advance, but for most problems, k is not given. So we have to determine the optimal number of clusters for k-means. A typical method for determining the optimal number of clusters of k-mean is called the elbow method or knee method. Using this method, we find the optimal number of clusters where the sharpest drop in the objective function is found when increasing the number of the clusters. This optimal number of clusters means that even if we keep increasing the cluster number, we will not lower the objective function substantially. So let's look at an example on the right. In this figure, we plot the number of clusters against the objective function for a specific dataset. 2 distances are used in k-means, which are the Euclidean distance and the Manhattan distance. Let's try to identify a reasonable elbow point for both curves. So we can find out that for the curve of Euclidean distance, a small number of clusters, around 5, are optimal. For the curve of Manhattan distance, around 20 to 30 clusters would be, in this case, the solution. This is also an example showing that the selection of similarity measures can affect the clustering results. In this lecture, we learned that a centroid-based clustering problem can be formalized as an optimization problem to minimize an objective function. And clustering results are dependent on the choice of similarity and dissimilarity measures. For k-means clustering, we assume the number of clusters given. It finds then the method k-clusters by iterating between the 2 steps, the E step, assigning samples, and the M step, updating centroids. And k-means is sensitive to the initialization of centroids, which determines if a global optimal can be found. In this end, we learn about the elbow or knee method that can help us to determine an optimal or a reasonable number of clusters for k-means. Now we are at the end of this lecture. Hopefully you can now formalize a clustering problem based on centroids and explain different measures of similarity or dissimilarity in clustering. And also you can now implement k-means clustering. So here are some reading materials that can help you to understand the content of this lecture and start implementing the k-means clustering. Thank you for your attention.